Let's try to solve this problem. A series RLC circuit containing a resistance of 12 ohms, an inductance of 0.15 Henry, and a capacitance of 100 microfarad are connected in series across a 100 volt, 50 Hz power supply. Calculate the total circuit impedance, the circuit's current, power factor, and draw the voltage phasor diagram. At this point, we won't be able to solve the power factor just yet. We'll go back to solving the power factor after we've discussed the lesson on power in AC circuits. So the given are the voltage source with a frequency of 50 Hz, the resistance of 12 ohms, the inductance of 0.15 Henry, and the capacitance of 100 microfarad. We are tasked to solve the total circuit impedance, the circuit current, and in order to draw the voltage phasor diagram, we also need to solve for the voltage across each of these circuit elements. So let's begin with the circuit impedance. Okay, the first thing that we can solve from here is the angular frequency, which is equal to 2 pi f. This is equal to 100 pi hertz. Okay. The next thing we will be able to solve is the inductive reactance. Inductive reactance is equal to omega L, okay, which is equal to 100 pi hertz times the inductance of 0.15 Henry. It's equal to 47.1 ohm. The next is the capacitive reactance, which is equal to 1 over omega c. So plugging in the known values of 100 pi hertz for the frequency, angular frequency, and 100 times 10 to the minus 6 farad, we get 31.8 ohms. Now the impedance is given by Z equal to the square root of R squared plus XL minus XC quantity squared. Plugging in the known values, we get 12 ohm squared plus 47.1 ohm minus 31.8 ohm quantity squared, and taking the square root of that, we get for the impedance the value of 19.4 ohms. From this, we can also solve for the phase angle. The phase angle is given by the inverse tangent of XL minus XC over R, which is equal to tangent inverse of 47.1 ohm minus 31.8 ohms divided by 12 ohms. Okay, this has a value of 0.9055 radians or 51.9 degrees. So this this means that the inductor leads the current and that this circuit is mostly inductive. Well, this is true because we can see here that inductive reactance has a greater value than the capacitive reactance. Okay, now we can solve for the current. The current is easily solved from this equation, V sub S over the impedance. Since V sub S is 100 volts and the impedance is 19.4 ohms, the current or the magnitude of the current is 5.1 amperes. We can now solve for the voltage across each of the circuit elements. The voltage across the resistor is easily solved from the equation I times R, which is equal to 5.1 amperes times 12 ohms or 61.2 volts. The voltage across the inductor is easily solved from I times X sub L, or 5.1 amperes times 47.1 ohm, which is equal to 240 volts. And finally, the voltage across the capacitor is I times the capacitive reactance, which is equal to 5.1 amperes times 31.8 ohms, or 162 volts. If you write down the waveform for the current, the resistor voltage, the inductor voltage, and the capacitor voltage, and the source voltage, we get the following. For the current, we have I is equal to 5.1 amperes times sine times 100 pi, this is omega, and then T. Okay. For the voltage across the resistor, we have 61.2 volts times sine 100 pi T. Okay. We know that there's no phase difference between the current and the voltage across the resistor. For the voltage across the inductor, we have 240 volts sine 100 pi T plus pi over 2. Okay, since the inductor voltage leads the current by 90 degrees. For the capacitor voltage, we have 162 volts sine 100 pi T minus pi over 2, since we know that the capacitor voltage lags the current by 90 degrees. Finally, for the source voltage, we have 100 volts times sine of 100 pi T plus the phase angle, which is 0.91 radians. We can now draw the phase plot or the phase diagram, and if you wish, we can also draw the sinusoidal waveform. So, by using MATLAB, I was able to program and type in the equations that I needed in order to make the sinusoidal plot and the voltage phasor diagram. In the sinusoidal plot, we have the current as this black curve, the resistor this blue curve, and you see that the current and the resistor are in phase. The inductor, which is the red curve, leads the current by 90 degrees. The capacitor, which is this magenta curve, lags the current by 90 degrees. And the source is shifted by 51 degrees. We can also see this in the voltage phasor diagram. The current, which is hardly shown here because it's behind the resistor, well, it's behind the resistor because they are in phase. The inductor has this magnitude and direction, or phase angle. The capacitor also has this magnitude and phase angle. Okay, the inductor is 90 degrees ahead of the current, and the capacitive reactance, or the voltage across the capacitor, is lagging by 90 degrees with respect to the current, and the source is about 51 degrees with respect to the current.